Okay, I actually put this together for expecting that Dick Calkins would be here to co-present this with me, but he couldn't make it.
Closer to the microphone, please.
He had some hip surgery, and flying in from Seattle was a bit difficult. This actually would, the first part of this is actually a continuation of what he presented last year, but he didn't present it at the conference. It's in his book. So I will continue with what was the experiment that he proposed in order to test this theory, and then playing off what he proposed, since he and I disagree on whether light requires source velocity, I came up with my own experiment. So I'll present these two here. And if you're interested in the details of Dick's experiment, I got his copy of his book here, and it's in much detail. I've had to summarize a lot of it. Does light acquire source velocity? Dick and I have had a friendly debate. Calkins says no. As per Maxwell's equations, it is released at a fixed point in space and remains anchored there as it propagates at speed c based only on the direction of release, not the source velocity. And there's a lot of people who hold to, a lot of dissidents, I mean mainstream obviously different, but a lot of dissidents who hold to that as well. I say yes. Again, apologies to my ether friends, this is a non-ether theory. Yes, since Maxwell's equations refer only to propagation relative to the source, which, if moving, transmits its velocity to the emitted light as well. Speed c relative to moving source only. And there's people who follow this as well. So I don't know what the proportions are, but I know that this community is split between these, and there's probably some other theories as well. Trying to illustrate this debate. At time zero, we have a light pulse is emitted, and we have a moving observers next to this. So we're going to have an observer next to a laser. We're on like a car or whatever. There's the target at time zero, and over some time interval, the laser moves here, the target moves here. So if light does not acquire the source velocity, the motion of the laser is irrelevant, and the light should travel straight up here. But of course, by the time it reaches here, if light does not acquire the source velocity, the target is here. And so if you were able to observe if the observer next to the laser was able to observe the beam, and I think this follows what Bob presented earlier, it would seem to have gone backwards. Now, if light does acquire the source velocity, then it has a vector sum of the c and the v, and it would travel this way. However, what would be observed by the observer who was here would be the straight line up to the top of the solid beam. So if we were able to actually perform something like this experiment where and again, because of the immense speed of light, we don't have the technology to really handle this, but maybe we do. I said Dick has proposed that we might be able to pull this off with today's technology. Maybe we could settle this debate, or maybe light does something completely different. I don't know. Dick's experiment, and this is just a very high-level overview of his experiment, but he basically proposes putting an optical laser with a beam of 100 micrometers focused up to 135 meters. He wants to use fiber optic cables, diameter less than 100 micrometers, accurate light sensors to determine when intensities received from two fiber optic cables are equal versus reversed, facing mirrors 1.5 meters long and 0.5 meters apart, with tolerances. He looked all this up, and these products are commercially available as they are today. So he's basically got a device here with a laser that shoots almost purely vertically, but just a little bit off, because he's trying to get a tremendous distance. He actually ends up trying to get about 134 meters for his light beam, and the only way he can do that in a practical way, and he's going to put this on an airplane, is to have it reflect a lot of times. And basically, if the plane's stationary, it bounces back and forth 134 times, and he sets up his light sensors so that when the plane is stationary, it hits the farther fiber optic cable, and what he believes is that once you put the airplane in uniform motion and you repeat the experiment, because he believes that light does not acquire the source velocity, in effect, the light beam will hit slightly behind where it hit when it was stationary. And for him, that's this other optical laser. So he has two optical lasers here with all the calibrations and the speeds, etc. His experiment proposes that if we conduct this first on the runway with the plane stationary and then in flight with this plane at a constant speed, that we would initially we'd see the light hitting this sensor, but once up in the air, the light would hit this sensor because it fell behind. If light does acquire the speed of the source, then we would see no difference. This same sensor would be hit both times. So that's basically that's the crux of his experiment. And again, he's got all the details and the measurements, etc. Here's some of the parameters he's looking at. One round trip, again, he wants to have a lot of round trips in order to get the length. And these are all the parameters that you can see in here, the distance between this. Using a jet aircraft with the laser and optical fibers aligned with the flight velocity vector, pre-align the laser so that the center of its beam is aligned at the center of the alignment detector when the number of round trips is equal to 134. He wants an even number so he didn't have to put the sensors at the top, he wants them at the bottom. And again, there's the two sensors. The one that's a little bit farther than the other one is the one that would, be this was Dick's arrangement. And so using a jet aircraft with the laser and optical fibers aligned with the flight velocity vector, he pre-aligns the laser so that the center of the beam is aligned at the center of what he calls the alignment detector, the slightly further optical fiber, for 134 round trips. Prior to takeoff, he fine-tunes everything to make sure that the maximum light intensity is recorded there. He takes a record of the light intensity on both the detector that's a little bit farther and one that's a little bit closer. He then establishes a straight, level flight path in the same vertical and horizontal orientation as when the laser was aligned, accelerates to 240 miles per hour. Again, the calculations as to why the specific speeds are in his book. Very slowly, he continues to accelerate until the alignment and test detectors have identically the same level of light intensity. So since he believes that this is what's happening, the light will lag a little bit because it doesn't pick up the source velocity. He believes that once he tries to reach a point where initially the light was hitting at this farther fiber when it was stationary, then at a speed of about 250 miles per hour, it's hitting between the two of them equally. So you would get equal intensities, probably half intensities on each one as the light slowly moves back towards the other fiber as the plane changes its speeds. So he records the aircraft's velocity and the light intensities to detect a specific velocity at which equal intensity occurs. And his calculations show that that's somewhere around 250 miles per hour. If light acquires its source velocity, my theory, the intensity at the alignment detector will remain unchanged and the test detector will remain essentially non-illuminated. If light does not acquire its source velocity, Calkins' theory, the intensity at the alignment and test detector should be equal at 250.2 miles per hour. He then continues to accelerate up to 490, then very slowly continue to accelerate until the intensities of the alignment and test detectors are precisely reversed from prior to takeoff. At this point, then the full intensity is at the detector that's slightly behind, and there's nothing at the one forward, because when he doubled the speed, they were equal there. It's moved back another 100 micrometers. If light acquires its source velocity, the intensity at the alignment detector will still be the same as before takeoff, and at the halfway point, the test detector will remain essentially dark. If light does not acquire its source velocity, intensities at the detector should be fully reversed at approximately 500.44 miles per hour. And again, this is how the optical path through the intensity compares with the vertical path. Basically, again, he's essentially created a vertical path here, but instead of having at 134 meters, which would be a little bit hard to handle on an airplane, he has it reflecting back and forth. After the plane reaches the 500 mile per hour mark, the light that initially hit here will hit here. 100 micrometers. And that shows that light does not acquire the source velocity. It's released from a point in space and stays on that vector. So, I tried to parallel Dick with another experiment myself. I came up on a rocket sled. And I looked this up to see if these were realistic values, etc. So, a rocket sled and the speed, if you look on this website here, they have accelerated rocket sleds to 2.8 kilometers per second. So I started a rocket sled at point A, I accelerated from point A to O, and then I decelerated to point B. How easily this is going to be done and the precision is another story, but at least theoretically it's possible. At point O, the rocket sled shoots out a pair of laser rays. It can be a beam split if you want to make sure that they're the exact same time, whatever, but it's exact same time. And so those two beams are then going to hit those two detectors. The detectors are each 7.5, it's 15 kilometers between detector A and B, so each light beam has to go 7.5 kilometers. To account for the curvature of the Earth, 6,400 kilometers, I actually have to raise the detectors a little bit, 4.4 meters, so that it's actually a pure straight line. When stationary, the laser rays each take 25 microseconds to reach each detector if it was at least at point 0. If light does not acquire the source's velocity, that's Dick's theory, both rays will reach the detectors at the same time when the rocket sled shoots the lasers at 0. Similar to special relativity, because the fact that the rocket sled is moving here is irrelevant because the light is released here and it just travels at c in both directions from the point of release independent of the source velocity. If light acquires its source velocity, I postulate the ray traveling from O to B, the forward direction, will pick up the speed of the rocket sled and will reach reaching B in 300,000, reaches B in 7.5 over 3 seconds. So it reaches B a little bit quicker than the ray traveling from O to A, which is going to travel at 300,000 minus 2.8, reaching A in, and I didn't write that out because it's a whole bunch of decimal places, but basically, if it picks up the source velocity, then the light beam is going to hit B slightly ahead of when it hits A. The difference in arrival times will be basically 47 nanoseconds. Theoretically, this is measurable by today's technology because I was able to find some sort of detector that is able to measure things in the fractions of nanoseconds. So I tried to parallel Dick by coming up with an experiment that theoretically could be done with today's technology. After going through this, I thought that maybe the Earth itself, and again, with apologies to my ether friends, this is a non-ether approach. The Earth moves pretty quickly through the, at least relative to the galactic center. I think it's on average about 220 kilometers per second. So assume light does not acquire its source velocity, that is, released from a fixed point in absolute space, in a straight line vector at constant speed c. The Earth's rotating at 0.5 kilometer per second, going around the sun at 30 kilometers per second, and the sun, the solar system's going around the galactic center about 220 kilometers per second. There is no stationary point in absolute space anywhere within our galaxy. I mean, if we limited our universe to our galaxy, and we called our galaxy absolute space, the only point within our galaxy with no motion whatsoever would be the absolute center. And again, if the galaxy is moving relative to other galaxies, we don't really have a reference point to determine the absolute space, but let's just limit to our galaxy. By definition, any laser light emitted on Earth, if not acquiring this velocity relative to our galactic center, should always veer off any vertical path. It need not be moving relative to the Earth's surface. Again, this is the theory that light does not acquire the velocity of its source. So I came up with this little example. Any object on the Earth's surface would move from 190 to 250 kilometers per second relative to this absolute space. It's the 220 kilometers per second going around the center of the galaxy, and the 30 kilometers per second, ignoring the half a kilometer per second from the Earth's orbit. Light that does not acquire source velocity should exhibit a rather profound shift from the vertical without its source moving at all relative to the Earth's surface. I mean, 250 kilometers per second is, what is it, 300,000? 1 e to the minus 4, I think it's 1 e to the minus 3, the speed of light. So it's 0.1%. I mean, that's not microscopic. I mean, it might be enough to get something going, to measure it. Light from a laser pointing vertically upward at the equator to a target 1 kilometer immediately above it at midnight, when the Earth and Sun lie directly in line with the galactic center, would have to veer away from the target as a result of both the laser and target moving together somewhere from 190 to 250 kilometers per second away from the initial emission point. So basically you've got the laser here, the target up here, and with the Earth's movement relative to the galactic center, if the light is emitted from the target and it is independent of the source, by the time it reaches where the target was, the target will have moved away from it a little bit. So you wouldn't, if you're up at the target, you would never see the laser because that beam never hit you. It fell off somewhere else. And that's the example here. The black, so this is the source. The laser is a rectangle. The target's a circle. It's moving away relative to the galactic center, and by calculations, if it's going to go for the time it takes to go 1 kilometer, it will have moved 3.33 microseconds after the green laser pulse is emitted. And for a stationary source, obviously it misses the target because the target's moved away. Independent of the source velocity, the light beam will travel at 300,000 kilometers per second over, here's the geometry here, over approximately 1 kilometer, so the travel time is 3.33 microseconds. The target and laser in perfect vertical alignment will have moved basically 0.0063 to 0.0083, or basically 0.6 to 0.8 meters away from the point from which the laser emitted its light. We can measure this. So is it observable? If we could find or construct a vertically clear span at the equator, or actually anywhere on the Earth, since the Earth's rotational speed is negligible compared to the speed about the galactic center, 1 kilometer high, can we find a sheer cliff that might do this for us? We may be able to settle the issue as to whether or not light acquires the velocity of its source. Certainly a shift of between 0.6 and 0.83 meters off the vertical would be indisputable. It just so happens that El Capitan in California is 900 meters high. And it tends to overshoot, so I mean theoretically maybe we could put a target up on the top of El Capitan, get a laser 900 meters directly below it and try the experiment. And then we would expect to see a shift 9/10 of what I calculated, 0.57 to 0.75 meters. That's it's like 2 feet, 2.5. I mean, that's certainly observable. So in summary, both Dick and I have continued to engage in a friendly debate over whether or not light acquires the velocity of its source. This is characteristic of a difference of opinion among many dissident physicists, and there may be other theories as well. We've both proposed experiments using current technology which might lead to a definitive conclusion, or else open up even more speculation if the results favor neither. And that concludes that talk. Yes?
That was a very interesting experiment where you had the beam bouncing,
Yeah,
so many
that's
bounces and
experiment.
you get that. And it seemed to me that would be a good thing if you can develop that. You'll have an optical velocity meter. You know, you can measure your velocity using optics, and that would work into an optical navigation system. You ever thought about doing that?
You'd have to. I haven't. Again, that was Dick's experiment, so we'd have to ask him about that. But his goal was to say, could we do something with the technology we have today?
Mm-hmm.
I took his idea. I said, well, why don't we put on the space shuttle? Because then instead of 500 miles per hour, we're going to get 17,000 miles per hour.
That's another one.
And then you're not going to be worried about 100 micrometers. You're going to be at 1 or 2 centimeters or something like that at a higher speed. So, but basically the same idea is to run his experiment up on the space shuttle.
Yeah, that's another idea.
So it has been quite some time that the optical gyroscopes are in wide use. So could you comment maybe the relationship between those?
I'm not familiar with
In my
with
view,
the use of
I'm not sure.
maybe someone here is more familiar than I
But
am.
in my view, actually, the optical gyroscope, that is in practical applications nowadays, is kind of form of the Michelson-Morley interferometer. So now,
There was
if
a
this
question.
working, then this would be working.
Yeah, you're responding to him?
Not really.
Go ahead. If you're responding to his question, if there's otherwise a new question up front.
Right. If you look at the Michelson-Morley experiment, there were three sources, the mirrors in a triangular pattern. And what happens, it turns out that whole experiment is sensitive to rotation. You can move linearly and you will not detect anything because the whole laboratory is moving along with you. If you believe in emission theory and light bounces off a mirror and the mirror moves with a velocity v, then the light has a velocity c plus v relative to the rest frame, not the mirror, but also relative to the mirror, it's always c. Yeah. So if you believe that, you have to stand up and defend it with your life, you know. So you argue that, then you'll find out, you know, that if you have a closed laboratory, you have no windows in that lab, there's no way you can know your velocity relative to the rest frame. There's no way you can know it because you have a closed system that's moving along with the rest frame.
Yes.
Yes, a very interesting experiment. This reinforces my conviction that light takes on the velocity of its source. Indeed, if light speed were constant, independent of the speed of the observer, it would have been impossible to measure because all measurements are relative.
Yes.
Yeah, one of the, people have tried experiments like this, and there's some interesting things that come up. So one I want to just mention is, you got the laser, and when you're still, and you align it by moving an angle of the laser until you get it to focus on the end.
Right.
But the thing that causes the beam to come out straight is the mirrors. Now, so when you take into account now the ether people, and look at it here, what happens is, as you start to speed up in the ether, and the ether's moving by, the bouncing angle changes and you don't know it. And if you assume it, you put the laser in and didn't move it, what would happen is it would adjust itself and you'd get a null result, even though it wasn't a null result, because it's a very, very ticklish thing. And I was going to ask Stephen if he would comment a little bit about it, because Stephen's written quite a bit about that Michelson-Morley. Stephen, am I getting you right about this? I hope I'm not telling you something. But the mirrors have an effect as an ether goes by the front of the mirrors and so forth. The mirrors start to change. Did I quote you right on that?
Well, the mirrors aren't. It might be easier if I tackle that tonight.
Yeah, because so the idea is that we think the mirrors just bounce off, but when you run an ether by the mirrors, they don't give us the old theory anymore, and they do it in a way that cancels our.
Yeah. Everything I presented is a non-ether approach.
Yeah, but
With ether, all bets are off on what I've been shown.
Yeah.
Two more questions over
Okay.
here. We're gonna just hold
Either one of
My brother and I did an experiment about 10 years ago, and also I mentioned the one on a boat. It turns out with a split photo detector, which you can buy, you can measure in the micron regions by building an electronic circuit around it. So you don't need anything longer than a meter even to do the detection theoretically. Now you got to watch out for noise effects and what have you. But really the split photo detector is just capable of really solving that problem. Much simpler than his bouncing laser.
I wish he was here. Yes.
Yeah.
I'd like to comment the fact that there's more, we're not discussing all of the options here. One option is there's no ether. Another option is there's an ether, but there's a third option, and that is the ether is attached to matter.
Ether direct.
Either direction.
And,
Yeah, back to the-
and but if you use the work that I do, for instance, all matter is made of electromagnetic solitons, standing waves of the field. So the field is intimately attached to matter. So anytime you have matter, and then you gotta look at the local effect and the long range effect. So for instance, when I'm on the Earth, what is the most significant thing that, for instance, affects gravity? It's our sun is affecting it. What about the Milky Way? Well, it's so far away, it's weak. And then if you take into account other galaxies, it's even weaker. So the local effect becomes prominent. But where's our experiment done? It's done locally. So we have to, that makes that, even though all these things are moving, the Milky Way galaxy and our sun and everything is moving, we don't see that motion because, in gravity, because the effect is too far away. Even though the mass is much greater, but the distance is much greater too. And so you have local effects, and if the ether is for instance the electromagnetic field, then that's going to dominate, and you won't observe some of these things you're trying to measure in your experiment.
Well, one more, and that's it, folks. We have time.
I was wondering if perhaps both postulates might be correct, in that the beam would be aberrated under acceleration, but once you stop the acceleration, it would not be changed. But if you re-accelerated it, even if you slowed it down under acceleration, again the beam would be aberrant.
Yeah,
So the acceleration itself would be the determining factor.
yeah,
Actually, Dick gets into that in some of his theories.
this is the point that I was going to make. When you are accelerating, you are deforming your experiment. You had the mirrors, and your experiment suffer a deformation because of the acceleration of force, and you got shifting and things. Right? You had to be very careful in the acceleration. That gets false results and stuff like that.
Okay, that'll be it. Thank you very much.